Welcome back, and let's us continue with one of the problem in LeetCode weekly contest number 290. About this is about returning the numbers of rectangle containing each point. So we are given a list of rectangles and a list of points, and then we need to return an array which describe for each point how many rectangles containing it. So the rectangles is described by this data structure LIHI when the bottom left of the rectangle always been 0, 0.0. So what it means, for example, here, every rectangles always going to be this quadrant because it is described by 0, 0.0 and the LIHI. So this is the LIHI point for each of the rectangle. Then they also kindly enough to give us the definitions in mathematical form of what does it mean by a point is actually contained by a rectangles. Basically, if the x point is in between 0 and li, while the y point is between 0 and hi. So these two conditions, it's an AND logic. Okay. Now, an example like here, point 1, 4 is actually contained only by the purple rectangles, while the next point 2, 1 is actually contained in two rectangles. One is the blue, the second one is the purple, because remember all the rectangles actually covering from 0, 0.0. So this purple is actually all this area. That's why this point actually contained by two rectangles. And then because this is the point starting 2, 1 and 1, 4, 2, 1 has two rectangles, 1, 4 has one rectangles. So this is the return. And for this kind of problem, remember to also look at and understand the constraint, because usually idea for efficiency come from understanding how to leverage the constraint. So this one, the length are can be quite big. This is just about the data structure. The x can be quite big. The y, this is unique. This is special because they say the y can only be up to 100. Why is that like that? So this is a thing that we need to remember when we try to think about ideas how to solve this. Then all rectangles are unique, all points are unique. This is another good knowledge. So we don't need to try to create a code that try to make efficiency of looking for duplicates and skipping it, because it's already guaranteed to be unique anyway. Okay. So how to solve this? One of the key point here is the definition itself. When we look at the definition like this, where it is about the order of x and y, we need to try to think and then try it whether ordering the input, sorting the input can help us, which it can. So if we sort rectangles in a descending order starting from the biggest, we can stop early, right? Because when we sort the rectangles starting from the bigger, when we already find the point x is not fulfilling one of the rectangle, we no longer need to check the next rectangle, because the next rectangle will definitely smaller. So how does this violate this condition when x is bigger than L? If we sort the rectangles from bigger to smaller, the next rectangle will have a smaller L. So why would we need to check it further? So sorting rectangle is important. Okay. And then the second efficiency comes from leveraging this constraint of 100. Why? Because we need to think like in dynamic programming, where we actually try to find a thing that we already can pre-calculate it. So for example, when we try to check one point here towards all the rectangles, Actually, at that same time, we can already check for all, we can already store the logic for all points which has x less than 2 between the points here and the y of the whole rectangles that is containing the x. So we can do that. It will be much more clearer later on when we write the program, because the way we track that, we will keep a data structure, basically just a list that will accumulate this, and then this list later on can be used to encode the final answers, which is the number of rectangle per points, right? Later on, once we got into the code, it will be clearer. But for now, let's go for it. First of all, maybe I will explain first about the efficiency that we can get when we try to order the rectangles in reverse order, descending order. So let's say that one is the rectangles and this is the point. So we check this one. 5 is less than 6, 2 is less than equal to 2, so this point is inside this rectangle. And then we check this one. 5 is bigger than 4. That's it. It's not in this rectangle. And we don't need to check this one because we know this is going to be smaller than this already. That's why we need to sort the rectangles in reverse order. And another thing just now is we need to sort the points too. The reason why we need to sort the points too, because we want to check the points starting from the biggest x of the point. And then because if we try to check from the biggest x, it means we already check for the biggest rectangle accommodations to it. And then the next x, the next point, when we guarantee that the next point of the x is smaller, we already know that we already calculated that, because remember just now the second efficiency idea is basically when we check for each point, we're going to already calculate the possibilities for all x that is less than equal to that x point. That's why we need to start from the bigger, so that when next we calculate the point with the smaller x, we can leverage what was pre-computed already when we calculated the bigger x. When we write the code, it will be much easier. But basically, we need to sort the points also in reverse order. But one tricky thing here is later on we need to return it in the correct order. We need to return the containment of the rectangles in correct order. So we actually have to create another variable, let's call it points_x, to hold the points and its original index. So basically we are going to do this. So P0, P1, that's action 1, and the index itself. Okay. Then we're going to use this and sort it. Now we already prepared everything. How about what to check? Remember just now we will pre-calculate everything, and that will be a normal list. This is where we leverage this constraint that the y can only be 100. So remember just now the idea is to pre-calculate everything within y for each point that is up to x. So we will at most need 100 of this because everything can be, oh, it always be 1 at least. So actually we just need 100, I think. Well, later on when we submit it, it fails. We know, but logically speaking, because everything can only be starting from 1, so at most there are only 100, what you call that, 100 points. Right. Then let's do it. Later on also we need to store the result, right? And the result will have the same length of the points. This is what we're going to return. Another thing is we're going to remember the leverage that when the next point doesn't need to check the rectangles that already been checked by the previous point. Now let's write the looping for the point first. We use the one that is having the index and sorted. So for each point, we will check for each rectangle. But we want to leverage the fact that we already sort the points so that we don't need to check the same rectangle. Because if the higher point, the point with the bigger x, already being checked, we don't need to check anymore for the points that have the same or smaller x, because we will already calculate everything. Let me show you what I mean by that. So in other words, we need to keep the index of the rectangle that we are looking at. Of course, it's starting from 1. And we need to sanity that it never goes beyond the maximum. And then we need to check that we only going to start filling in the memo, calculating everything when the x is less than equal to the rectangles Ri x point. If this is true, we're going to calculate for all possible points in the rectangles. So notice here, I'm using the rectangles, not the points. So to make it clear what I mean by that, for example, when we go to here, the largest x will be here, so it will be starting from here. So when it goes to here, it will check for each rectangle first from the biggest rectangle, right? Then when it checks from the biggest rectangle, it will calculate all here, all the y here, it will plus 1. It means all points where the x is less than equal to here and the y is the corresponding y, it will be contained by this rectangle. Then at the second rectangle, the same logic happening. For it, we will calculate, we will do another increment to the memo plus 1 for its index that is representing the y. From y here to y here. To be exact, I'm only setting from 1 because the points can only be started from 1 anyway, so we don't need the 0 in the 0 value. Okay, so that's the idea. So the memo index of the memo is actually reflecting the y, while that's why we actually for each point we actually do this calculation. So the memo ry will be plus equal to 1. At the end of everything, when we finish with this, we need to increase the ri because we already finished calculating the rectangles and we don't need it anymore. This is the reason why we can make it don't need it anymore. The second reason why we can make it don't need it anymore because we already sort this from the biggest x and the point, right? So it's incrementally built up. The biggest x built result will be used to build the next smaller x of the point. So that's how it is. And at the outside, after we do everything there, we can already know the result for, oh, just now this one also have the index, remember, so that we can keep the order of the point. We can know the result for that point by accessing the y. So here, yes, it is that the x of the rectangle doesn't mean necessarily that the point is inside the rectangle, but we know it, we doesn't care about it because we calculate all the possible y of the rectangle. If the y is within the ry here, definitely it will have a value. If it is not, then it will have the 0, right? So that's why this works. But this is actually not efficient if we only have a problem like this. A very sparse, only 2 points. But remember, in the constraint, we can have this many problems. When we have this, we do this, is actually make us faster. Why? Because the y is only 100. So it's just cheaper to pre-compute it all the 100 rather than trying to go through all possible 10 to the power of 4. So if you only look at this problem, you will think that this is not a smart move. Yes, it is not if all your problems are like this. But we know that it is not. We have to solve this problem. And when this problem comes in, this becomes far more efficient because we only calculate 100 of it. First of all, let's test it. So it looks correct. Now let's submit it. Runtime error. List index out of range. Oh, right. Because I'm using a non-zero index. So I need actually 101, so I have index 100. Cool. The reason why we need that, so that I don't need to do like y minus 1. So I'll just make this 101. The 0th one actually never going to be used, but it's a small footprint out of many of this. And that's how we solve it. So remember that the idea is actually to sort it and then sort the point too. But for the point, we have some speciality here that because later on we need to keep on the order of the result, we sort the point just because we want to make the efficiency. Then we prepare this memo where we actually, the idea is because of all this ordering, we can actually calculate all the y for each rectangle already, so that the next point check will build upon the previous check. Hence, for each point, we actually checking the next rectangle. We don't check the same rectangle twice. That's how this is become efficient. So now the time complexity, right? Sorting like this, definitely, let's say the length of rectangle is n, and m is the length of the points. Okay, the time complexity from this one is will be big O, and this one is big O m. Like this one is big O, sorry, this one ordering, so big O n log n, m log m. This one is big O point is what m. Okay, and then this one just one, just consider it as 1 because it's always 101. This one is m, so this one is big om. There is an inner loop. Well, for this inner loop, it will always be just 1. Why is just 1? No, it's not just 1. This is as much as it's still fulfilling this, but remember that this ri is carry forward, so actually the whole while here is not, this one is definitely can go up to the n, which is the length of rectangle, but when we combine the loop, this is doesn't mean m times n. This is actually m, this is just m points plus n. Why plus? Because we carry forward the ri. So the each point will never test the same rectangle. So in total, we only going for each point, it's only going to test the n. So it's actually this is big O and between the max of m or n. Okay, that's what going to happen here. Oh, no. This one will be, okay, this one actually big O. We can say big O1 because at most we know that the Y at most can only be 100, right? So this is kind of big O1 if you want to think about it. So this is can become 100n. So for each point, it will, for the total of each point, it will do 100 times n. N is the rectangles. But it become a max because remember, for each point, it won't revisit the rectangle. That's why it's not multiplication. It's not m times 100 times n. But it's just the max. Which one is the maximum? That will be the, which one is the bigger one? That will be the one that overshadow the others. Because for example, if there is only 1 point, but there is like 10 rectangles, right? So it means that at worst case, it will goes through 10 times 100 if the y exists exceeding 100. But if it is like 100 points and the rectangles is only 1, oh, there is 1000 points and the rectangles is only 1. We know that for each point, it will only start going here if it fulfilling this condition. But once it fulfills this condition, that's it. We don't need to do anything anymore. So this one will only run 100 times if it only have one rectangles. Worst case, only going to run 100 times. While this one, it will goes 1000 times when we have 1000. So this part will go 1000, but this while loop will be skipped, right? Because this can only be fulfilled at most one. It can be nothing fulfilling this also, but at most one. That's why it's a max between here. Now the final big O notation will be the summations of everything from top to bottom. Log n plus m log m, 100, m, and for this one we took the top one, not the inner one. The inner one is just used to actually determine this one. So in this case, the worst case, if the number is quite big, because that's what big O means, will be the maximum between n log n, m log m. Because 100 is like a constant, right? And this one is just m and n. So the sorting is actually the expensive part. So that's about it. That's how we solve this problem. This is one of the more difficult to explain, basically difficult to explain the idea, because but in order to get the idea itself, basically remember to find insights from the problem, find something weird, and then try to think about a way to leverage this. The pattern we use to leverage this is basically sorting data. That's why if you go to computer science schools or what, you will always learn this sorting algorithm, because that's usually one of the key points to solve a problem, to make it more efficient. Try to sort it. It's almost similar with life sometimes. Your life sometimes can get easier when you try to sort your life. Try to tidy it up. Okay, so basically that's about it. If you think this is helpful for you and you like it, please click the like button and subscribe. Thank you so much.